So our final contribution today is the Harold Jeffreys Lecture for 2017, and I would like to take the opportunity before the speaker gives the lecture to present the citation, since Tim Wright wasn't at the awards ceremony. So could I just read the citation? Bear with me, please. Professor Wright of the University of Leeds is an outstanding researcher and world leader in the field of applying satellite radar interferometry, INSAR, to measure tectonic and volcanic deformation. He's the director of the UK-wide NERC-funded COMET, the Centre for the Observation and Modelling of Earthquakes, Volcanoes and Tectonics, and principal investigator on a number of other large collaborative projects. His research highlights include the first demonstration that interseismic strain can be measured using INSAR and the discovery of a major continental rifting episode in Afar, Ethiopia. His ability to communicate complex multidisciplinary problems to the public is evidenced by multiple television appearances on the BBC, both news and documentaries, and the Discovery Channel productions, in addition to extensive outreach activities. He was selected as the British Geophysical Association's Bullerwell Lecturer in 2015 and has also received awards from the Geological Society of London, the American Geophysical Union, and the University of Miami. For these reasons, Professor Tim Wright is awarded the position of the Royal Astronomical Society's 2017 Harold Jeffreys Lecturer.
Thank you very much. That's very embarrassing.
Did you write it?
I didn't write it myself, no, but I probably employ the person who did. So, right, let's see if we can get my computer to talk to the screen. And okay. Okay, here we go. So, I want to talk to you about modern methods in satellite geodesy, and so we just heard about positioning in the 18th century, where we were getting to the nearest degree. With modern satellite geodesy, we can locate ourselves to the nearest millimetre now. So we've come on a bit, and of course we're using those techniques to really reveal how the Earth is deforming. I want to show you some highlights of some of the work we've been doing within COMET. And particularly I want to, let's see, is this not, there we go. So I just highlighted that red to remind myself to thank my collaborators, and I'll try and identify the people who've done the individual bits of work as I reveal them as we go through. So I guess the motivation for this is to do with earthquakes. So earthquakes have killed nearly 1 million people since 2000. This is a photograph from last year's earthquake in Italy, in Amatrice, that killed about 300 people. This is from Haiti in 2010, an earthquake. Actually, it's very difficult to estimate the number of people who died, but somewhere between 100 and 300,000 people died in this earthquake, a really devastating event. And of course, volcanoes, we'll all remember that the unpronounceable eruption from 2010 that caused such widespread devastation. So what I want to try and demonstrate is how we can use modern methods for measuring how the Earth deforms to try and both understand the processes that are causing these events, but also to monitor locations and say something about future activity. So there's 3 parts to the talk. Well, the first, I'm just going to introduce the tools. And then talk a bit about event response. So what do we do when an earthquake happens or there's a period of volcanic unrest? And then I'm going to talk about how we do long-term monitoring. So last week I was at a meeting to celebrate the 50th anniversary of the discovery of plate tectonics, and one of the things everybody knows about Harold Jeffreys is that he famously didn't believe in plate tectonics. He was very much against the idea of continental drift right up until his death in 1989. And here's a nice quote. I think this is from the first Harold Jeffreys lecture delivered by Harold Jeffreys in 1963. And he concludes that you know, this information that's in newspaper articles and scientific journals are remarkable for fallacious data, misinterpretations of data, and omission to mention any objections, which is pretty strong stuff. And actually does talk about surveying and positioning in that lecture. And at that point, there hadn't been any clear measurements of present-day motions of the continents from surveying techniques. And he quotes Markowitz, who was a geodesist at the time, saying large shifts occurred until we had the telegraph, and then once we had that, we got moderate ones until the invention of the radio, and then now we can't measure anything. Now, of course, we know that that's not true, and that we've now got much more precise tools for measuring these motions. And I want to talk a bit about those tools. The first of which is global navigation satellite systems, the most famous of which is GPS. And this is a very simple system, really. It relies on satellite clocks orbiting, atomic clocks orbiting around the in orbit on satellites, and essentially transmitting the position of the satellite and their time. You record that on your phone, in your GPS chip, or in your car, or with your GPS receiver, and you can then do a calculation. You need 4 satellites to get a position. You need 3 for your X, Y, and Z position, and then a 4th because you don't have an atomic clock in your phone. I'm just going to start my timer here, which I forgot to start, so I don't overrun too much. So with this, by tracking, so these were designed, they send a signal down, and if you use the code, so your phone can position yourself to about 4 or 5 meters instantaneously. But if you track the carrier phase through time from those GPS satellites, and you record that, and you're very careful about all the corrections for the ionosphere and other sources of noise, you can position yourself to about 1 millimeter. And there's now a suite of these systems. The one that's being developed from Europe, Galileo, there's a Russian system and a Chinese system, etc. This is what you do in practice, is you go into the field in places like Afar in Ethiopia, and you operate these in one of 2 ways. One is you'll install a marker into the ground, and that's just a pin, and then you locate your GPS receiver, the antenna very precisely over that pin, and you come back periodically to see where that pin has moved to. The second method is you'll install a permanent, or in this case semi-permanent, because the Afaris would like to steal our GPS receivers. What you hope is a permanent installation, in this case operated by solar panels that record the signals from the satellites and track that position continuously. From that, you can get these spectacular maps. So this is a selection of GPS data from a compilation from 2014 of around 20,000 GPS sites. So this is a huge collaborative effort from the scientific and surveying community to collect these observations. And it really is a spectacular demonstration that the continents are indeed moving. So you can see here, that's the Arabian Plate. These are in a reference frame relative to stable Europe, Eurasia up here. You've got India moving up there, colliding with Eurasia. You're seeing this huge amount of deformation caused by that collision over a really wide region. There's huge amounts of information. I could just probably talk about that for the rest of the lecture, but I'm going to try and zoom in on a few highlights. So the other technique was mentioned in the citation is one I've worked on during my career is a technique called interferometric synthetic aperture radar, or INSAR. So this is a technique that essentially uses an imaging radar from an orbiting satellite. You send down a radar wave. This is not to scale, this diagram. The satellite's at 600 kilometers, and typically we use wavelengths of around 6 centimeters. You don't know the total number of wavelengths precisely enough because of noise from contributions from the tropospheric delays, from the ionosphere and other sources of noise. But you can track the changes in that path length very precisely. And so you look at those changes and you can make maps of those changes in path length that really give us this very precise images of how the ground moves in between the two radar acquisitions. And there are systems now like the EU Copernicus Sentinel-1 constellation that are really acquiring huge volumes of data systematically over the continents and enabling us to respond rapidly to events and monitor the globe. This is what the data look like. This is from some data from, this is actually an aftershock of one of the earthquakes in Mexico from a few weeks ago, a magnitude 6 earthquake. That's the signal there. And the way to interpret these are like patterns you see on oil, these interferograms. Each of these interference fringes is basically half a radar wavelength of surface deformation, of change in distance between the satellite and the ground. If you move the ground half the wavelength, the total path length there and back increases by a whole wavelength. So in this case, the centre, I've really drawn those really badly on there. I'm going to rub those out. The centre there has gone down by 1, 2, 3, or 4 interference fringes. Each one's about 3 centimetres. So you've got about 12 centimetres of subsidence there that you can relate to this normal faulting earthquake that happened towards the base of the crust in this case. And we're processing now data over vast areas and putting those results out. You can go on our website and download those data we put those out as soon as they're processed. So we're really trying to automate this and make this much less of a black box than it used to be. And our aim is to monitor all of the tectonic belts and global volcanoes. Okay, so I'll start by showing then some events that we've responded to. And a couple of earthquakes and then one volcanic example. So here's some CCTV footage from Nepal. It's just before midday local time on the 25th of April. And if you watch carefully as I start this video, and you can watch this leaf start to shake. That's the earthquake that hit Kathmandu at this time. So the shaking just starts about now. It's just starting to vibrate there. And then you'll see people running out of the buildings as they feel that shaking. And then suddenly you'll see this very large movement as people are like they're on a deck of a ship as the earth is moving underneath them. It's a really astonishing piece of footage. You'll see this tourist here who steps over people on the floor taking photographs, which is... I'll show the video again. This time, this image in the top right is from a continuously recording GPS station. The scale here, that's its position at the start of the time series. This is just a map view, north that way and east that way. The scale, that's 1 meter there if you can't read the scale. And you'll see the movements that are causing people to be so dramatically affected on the ground in the earthquake. So here we go. We've got the shaking starting. You've got a little bit of movement to start with. And then here we go. We've got this really big displacement, and suddenly people are sweeping around. And you can see the position of the Earth's surface is moving on that kind of meter scale during this earthquake. And really, the motion to be very nicely synced up with the motion that we record in that GPS station. And you can see it'll settle down towards the end of this video in the centre of that circle, and that ends up being a total static offset. That point's moved by more than a metre to the south-southeast during the earthquake. So how do we traditionally respond to earthquakes? Well, we use seismology. It's still the main way, and it's still the fastest way we can get information about an earthquake. So for this earthquake, the USGS got their first location within 19 minutes of the earthquake, which is pretty remarkable, actually, that you can do that now. And there's some details about the location and the magnitude there. So they estimated initially a magnitude 7.5, and they're able to produce these preliminary maps that show the intensity of shaking on the ground. So the red colours are the amount of shaking that's predicted from the earthquake. After 52 minutes, they produced the first update, and they increased the magnitude to about a 7.9. And remember, this is a log scale, so that's a big difference. That's about a 4 or 5 amount in terms of energy. 83 minutes changed slightly. 2 hours didn't change very much. The first big change really was version 5 here. It was about 4 hours after the earthquake. And this is when they realized, when they first took into account the fact that the earthquakes aren't point sources. Earthquakes need fault planes to rupture, and to have an earthquake that's about a magnitude 7.9, you need a big piece of real estate to fail. You need a fault that's around 100 kilometers or so across. And so this is what we have from seismology. And by the end of the first day, about 15 hours after the earthquake, this was the best model you could get for the earthquake from seismology. So a very big piece of the Earth had moved. Kathmandu is there in the center of this map. But the picture's quite blurry. From seismology, from global stations, you can't get a very sharp image of what happened on the fault plane. And this is where the satellites can be really, really powerful. So this is an image, this is an interferogram we got within 4 days of the earthquake. This is the first time that Sentinel-1 passed over the location. And remember, these interference fringes, each one's worth about 3 centimeters of ground motion, and you can see they're very, very close together there. The contours are very large. So you've got more than a meter of displacement in the center here. It's easier to display these if we unwrap the phase, so we present this as a continuous field. Those red areas there have moved towards the satellite by over a meter, and to the north of that they've moved away from the satellite. And this is the classic pattern you expect from slip on a shallowly dipping fault. If it slips, you end up with the shallow part going up and the bit deeper going down. And so this was a confirmation of the mechanism. But from these data you can also do an inversion and get a sharp picture of what happened on the fault plane. And so this is work done by John Elliott in COMET, and he was able to then invert for this pattern of slip. So this is now a 3D view of the fault plane. So we're looking, okay, what's happened there? I need to log in again. So sorry about that. Maybe I'll plug in so it doesn't, I did prepared with a power source, so that might. There we go. Okay, let's hope that stays on. Sorry about that. So this is looking from the northeast, and we've cut away the material overlying the fault, and that fault underlies all of Nepal, and it's the Indian plate that's being subducted underneath Tibet. And this patch of slip we could image was the patch that slipped in the earthquake. And of course, I think one of the important things here is not just the bits that slipped, but the bits that didn't slip. And in this case, this part here, we know from other GPS observations made between the earthquake that section is locked. You can see the bending of the plate that's been taking place over the last 10 or 20 years with GPS measurements. So we know that at some point that's going to fail in an earthquake. And actually it was a big surprise in this earthquake that part didn't fail. So this earthquake only really did half the job. And the seismic hazard for Kathmandu, which is located around the edge, or somewhere around there, is still extremely high. And really what I wanted to emphasize is we got most of this information within a few hours of having that satellite data. So we can do a lot of this work really, really quickly now. Does it change the predictions? Well, yes. So we gave those observations to the USGS. They reran and updated their seismic shaking map. And you can see in this case there's quite a significant difference. The INSAR shows that the deformation is much more concentrated. And if you look at the shaking around Kathmandu there, then it's much, much higher with the model you get when you incorporate the satellite data. You can also use the observations, the data directly to get estimates of which buildings were damaged. I'm not going to talk about that too much. That's work from JPL. The media just seemed to care about whether Everest went up or down, and actually probably went down a tiny bit, but not very much. Okay, so I want to move to New Zealand and talk about an earthquake that happened last year in November. This is a really incredible earthquake. So this is a very famous house, poorly located on the fault rupture. The fault went right through there. And actually, it's a testament to how well built this was. It was completely ripped from its foundations and yet didn't collapse. I think there were people inside this building. And it's a very large earthquake. Only 2 people died in this earthquake. There was something like 10,000 people died in the same size earthquake in Nepal. So there's about a 10-meter offset there for that fault. Really incredible slip. The media get interested in very funny things. In this case, they were obsessed by these cows who were stranded on this landslide surface, and they had to be rescued by helicopter at enormous expense. And the farmer obviously had other ideas for how to deal with them. But anyway, so this is a case where the satellite data completely changes the view of the earthquake. So this is a view from seismology. So the seismologists got this completely wrong. They thought that this was slip on the subduction interface underneath the South Island of New Zealand there. When we got the satellite data, in this case within a couple of days, and we put the results out from the satellite to Twitter, it takes us about 4 or 5 hours now to get those data out, which back when I was doing my PhD, we used to have to wait for the tapes to be sent in the post and all those things. So it makes me sound old, doesn't it? But it's really remarkable what we can do now. But you can see just from looking at the INSAR data, this is a slightly weird combination of unwrapped and wrapped together, but a huge amount of interference fringes and a very complex network of crustal faults that have failed. So completely different to the seismology. Okay, so yeah, so what we can do this? Well, that's without the radar, that's with the radar. Completely different earthquake in this case. So we have a much better information about what actually happened. And we were working with partners in New Zealand at the GNS in Wellington. They were able to take our data and then use that in their daily briefings. So they're geologists who were able to go out into the field and actually use it to locate where the fault ruptures were and to go out and measure them. Some really spectacular fault ruptures in this case. Really beautiful and a dramatic earthquake. We were also able to use it to build a slip model like we did for Nepal, and then use that to estimate the stress changes on the other faults. And in particular, there's concern about the subduction zone interface to the north, some of which has been stressed. But probably the most significant impact is the way this earthquake has changed our view of how earthquakes behave. So this is probably the most complicated earthquake that anyone has ever imaged with modern methods. It broke this complex network of faults, some of which were mapped, and New Zealand has some of the best fault mapping in the world. So something like 80% of the faults that failed were known, but about 20% of them weren't. One of the things that was surprising was that there were gaps between the ruptures and between these fault segments. So the earthquake seems to have jumped from one segment to another in several places, and those jumps are bigger than 15 kilometers. And in many seismic hazard models, including the latest codes for California, that's this USERF 3, earthquakes aren't allowed to do that. They're only allowed to jump a maximum of 5 kilometers. So we've shown very clearly that you can have much, much bigger jumps. In fact, we've got another example from a different earthquake where there's a 50-kilometer jump. And also we had subduction zones and crustal faults moving together. So we do think there was some slip on the subduction zone interface. So I think the lesson here really is that we haven't had this kind of quality of data for that many years. We've got something like 100, 150 earthquakes where we've got good images of what happened now in those earthquakes. And so we're still at the point where we're being surprised by how the Earth behaves. Okay, I'm going to give a volcanic example again. So we're going to move to the Galapagos. This is some work we did. Marco Bagnardi, who's one of our scientists within COMET, did in response to a request from the Ecuador government, who are responsible for monitoring volcanic activity in the Galapagos. And they were concerned because a series of earthquakes had happened down here. And so we were able to, they contacted us, we were able to look at the interferogram from Sentinel-1 very, very quickly. In this case, a slightly unusual and unexpected pattern. We had this area here had gone down, and this area had gone up. And what this showed us straight away was it was consistent with the lateral movement of magma in the subsurface. So it wasn't showing magma coming up close to the surface, meaning an eruption was imminent. It was showing the magma was instead intruding sideways. So this was good news, and we were able to pass that information on, and actually that was used to lower the alert level in this case. So in this case, it took us, I think, it took Marco, I should say, I don't claim any credit for this work. It took him about 6.5 hours from the request to sending back the data with this interpretation, and another 4 hours he had a full model explaining the observations. So we are really now at the point where this is sort of semi-operational. If you've got skilled users, we can get these results very quickly, and they can be useful in real time. Okay, so let's think about monitoring in the long term. So it's all very well responding to the events, but actually, what everyone asks when you're at a dinner party, you're talking, you say you're a volcanologist or you work on earthquakes as well. Can you predict earthquakes and eruptions? And of course, we get very nervous about the P word. We don't even like to say it. But it's very challenging, and you can pick down what people really mean by prediction. And of course, what we really want to know is what's the probability of events happening as a function of space and time. And deformation can be useful for that. So volcanoes, it's relatively easy. This is Mount St. Helens. For volcanoes, they tend to deform when they erupt, before they erupt. So you've got to get the magma from the subsurface out. And when the magma is moving, it tends to deform the volcano. There are some exceptions, but in a compilation was work by Juliet Biggs and Susie Edmeyer and colleagues. They found that there's about 50% of volcanoes that deformed, erupted, and also if you didn't observe deformation at a volcano, then it probably isn't going to erupt. So this is a fairly useful diagnostic. It's not useful enough to say deformation means you're definitely going to erupt. That example from the Galapagos is a good example where actually the deformation shows there isn't going to be an eruption, imminently at least. But it's good enough to say, okay, something's going on here. Let's put our instruments out on the ground. There are something like 1,500 volcanoes above sea level that have been active in the last 10,000 years, and only about 100 of those have any instrumentation on them at all. And so this is a really useful way for monitoring all of those volcanoes and saying, okay, something's going on over here, let's get our instruments in and respond to those events. And it can be useful again in real time. So if we go to Iceland, this is an example from Bardarbunga, which was an eruption that took place in 2014, actually, and continued into 2015. Somewhat complicated diagrams. I'll try and talk you through it. There's various bits of information shown on here. The dots are the locations of earthquakes, and the colours of the dots tell you the time, the day of the earthquake. So the pink ones are the first ones, and we move through to red, the later sequence. And you can see from the colours of those earthquake dots that the earthquakes start here and gradually migrate that way. And what they're doing is magma is moving through this underground system here. It's coming out of that central volcano, being intruded through a dike in the crust towards an eventual eruption site that's over here. Now, the Geodesy was a key part of that monitoring as well, and so these arrows show GPS stations, and they show again the positions, their position tracks, a bit like that Nepal video I showed you early on. And obviously, they've again been dramatically exaggerated. There's the scale there. We've got up to about 0.3 meters of motion. But what you can see is as the magma moves, if we look at this site here, the direction and motion of those GPS sites swings around through time as magma is intruding into different locations. So the local monitoring organisations were able to use all of these data together, the seismology and the geodesy, to really pinpoint where this eruption was going to be before it happened. And in fact, Bob White at Cambridge was involved in this, and he put out a network of seismometers right on the spot where it was about to erupt. In fact, he had to move some of them because of the lava. So volcanoes, we can do a lot before the event happens, and that's really powerful. Earthquakes, it's not so easy. We don't think there's any obvious deformation precursor, or in fact probably no systematic precursors of any kind for earthquakes. And assessing the hazard is difficult, so particularly in the continent. So we've got wide plate boundaries. So here's again the Alpine Himalayan belt, where you've got the collision of Africa and Arabia and India, all colliding with Eurasia, creating this kind of big crumple zone. It's a really broad region. That's 2,000 kilometers across there. And you've got earthquakes distributed throughout that zone. Earthquakes are also pretty rare. So if you look at different time periods, we haven't sampled all of the earthquakes. So many faults might only fail once every 10,000 years, for example, in some of these areas. So you can see that by looking at different earthquake catalogues. The red dots here are earthquakes measured with really good global network between 1976 and 2015. If you look back with slightly poorer quality data, but for the big ones, the locations are pretty good back to about 1901 from seismology. You can see there's whole areas here that haven't had earthquakes in the past 40 years or so, but did have earthquakes in the historical period. And then you can go back further, another about 1,000 years with historical records. These are somewhat more limited. They're only the biggest earthquakes and only obviously in places where people live. But if we just put those on and off, you can see, for example, if we look at the Dead Sea Fault, there's had hardly any earthquakes in the last 100 years, but in historical period really lit up with earthquakes. So if you're trying to use the past earthquake activity to say something about the future, then it's challenging. And we know also from maps of active faults, these black lines on here are active faults, and you can see there are still active faults around here, some around here, and other places that haven't had any earthquakes even in historical times. So actually using historical earthquakes is challenging. And actually it's also very difficult to map the faults in the field. So sometimes to wake people up, I get them to try and work out where the fault is in that particular field. Test your tectonic geomorphology. Everyone got it? Everyone see where the fault is? So it's sort of through there. It's pretty subtle, right? So well done if you got it. I mean, the geologist standing right next to it was the clue. That's my colleague Laura Gregory at Leeds. But yeah, it's a pretty subtle feature. This is a fault in Mongolia. Probably had a magnitude 7 earthquake on it about 2,000 years ago. We don't know where all the faults are, so we're still being surprised. And actually, that's a real contrast to volcanoes. So volcanoes are easy, really. So there's only about 1,500 of them on above sea level. We know where most of them are. They're point sources, and of course, we have this precursory activity at them. Whereas earthquake faults are distributed over this wide area. We don't know where they all are, and they have no precursory activity. And so actually, earthquakes are much more deadly than volcanoes in general. And this is fairly sobering statistics. So 20 seconds of shaking in Haiti in 2010 killed about the same number of people as all volcanic eruptions in recorded history, which is a pretty remarkable stat. People normally query me on the stat, so this is the first time I've used it, and I've put the sources on this time. So, so the number of people who died in Haiti is somewhat debatable, probably between about 130 and 180,000, and about 220,000 people died between 1783 and the present. And that the authors of this particular study estimate that was about 90% of all recorded deaths throughout history. These are somewhat challenging numbers to get, but we've had 1 million people died just since the turn of the century in earthquakes. So earthquakes are clearly much more deadly, unless we have a really big eruption, of course. So how do we traditionally do seismic hazard analysis? Well, the most common method is a technique called probabilistic seismic hazard assessment, and this has been a really powerful technique that's really saved thousands of lives through implementing better building codes in countries like California, Japan, New Zealand, Chile. But it has some problems. So the way it works is you need a seismic catalogue. You need some ground motion prediction equations. So these are equations that say if an earthquake of a certain type happens in a certain location and you're a certain distance from that in a certain soil type or rock type, you'll experience a given amount of shaking. So they enable you then for each earthquake to make a prediction for how much shaking you'll expect. You also sometimes include knowledge of faults in this. You bring all that together and you can calculate the likelihood of experiencing a certain amount of shaking in a certain period of time. Now, the predominant input to this is the seismic catalogue, and so it relies on what's happened in the past, and it fails where the catalogues are incomplete. And there are many places on the world where the catalogues are poor records of what's happened, what's likely to happen in the future. Haiti was a very good example where the global probabilistic seismic hazard model, in fact this model here, has a very low hazard around Port-au-Prince in Haiti, which clearly wasn't true. So can we do better? And I want to try and convince you that we can do better if we use deformation. So we've known for more than 100 years that earthquakes are related to strain. So here's a simple cartoon of the earthquake deformation cycle. If we take a block of real estate, we deform it between earthquakes. We're basically putting elastic strain energy into the crust. The earthquake happens, that strain energy is released, you get rebound, and centimetres to metres of motion happening in a few seconds. So the idea is, so actually a digression, so this model is commonly attributed to Harry Fielding Reid, who made observations after the 1906 earthquake, but actually Richard Oldham, who was a seismologist working for the Great Survey of India, actually made these observations and talked about this after the 1897 Assam earthquake, so before the US model. And so I thought I'd put this in because there's another Harold Jeffreys quote. So Oldham was really a geologist. Geology was his passion, but he did some really fundamental work on seismology. And so Jeffrey says he was the only man I've known who did first-rate work in a subject that did not interest him. I think that's a nice quote. Actually, Oldham's real insight was from the faults in Scotland that he'd seen in the field as a geologist, he hypothesized that slip on a whole fault plane at depth in India had caused that earthquake. And then he was able to use the trigonometric data to show how the ground had moved. A remarkable piece of work. What we can do, though, now, and the hypothesis is if we could actually measure this warping with sufficient precision, then it should tell us where the earthquakes are going to happen. Rather than looking at where the earthquakes have happened in the past, if we can actually look at the warping, it should tell us where they'll happen and roughly how often. And there's good evidence that this can work. So this is two maps. On the right is the strain rate measured in California from GPS. So this is just the magnitude of strain. And you can see all the main tectonic features here. This is the San Andreas fault system here. And this is the Basin and Range and the Wasatch Fault here. So all the major things are shown as straining regions. A very nice correlation between the geology and the geodetic strain. But also on the left there, you've got the rate of seismic activity. And again, you've got a really nice correspondence. You can see those three main areas again showing up in the rate of seismic activity as well. So there's good evidence that this should work. And back to this map, we've got this beautiful data for the whole world, actually, but I'll show you a calculation of that strain rate model done by Corny Kramer and his colleagues at the University of Nevada in Reno for the Alpine Himalayan belt. And you can see this quite heterogeneous distribution of strain, but you can see some of these big features. There's the Himalayan front, nice and red. You've got some of these big faults coming off Tibet. Here you've got the North Anatolian Fault in Turkey. This is the Tian Shan. So there's a distribution of strain. There's also regions with relatively lower but diffuse strain, and then regions that appear to be fairly undeforming. So quite a heterogeneous map that you can use to try and say something about the distribution of earthquake hazard. And Bird and Creamer published a prediction of earthquake seismicity rate. So they work in rather unusual units. So they work in these units log to the 10 of epicentroids per square metre per second, which maybe in the RAS people think in those sort of units. I don't. So I've translated it for you here. So green is one earthquake per century in a 100 by 100 kilometre region, and then that's a logarithmic scale. So yellow and red are orders of magnitude more seismicity. And if you then plot the earthquakes that happened in the period beyond their training set, they get a very nice correlation. In fact, these techniques now are about as good as on a global scale as using historical seismicity catalogues. And as the data get better, they should give us an improved result in the future. And of course, by combining these data sets, you can do even better. But the GPS observations are still relatively sparse. So this is the locations of GPS in the India-Asia collision zone. And there are still large gaps where it's difficult to get instruments in. And actually, even where they look relatively dense, the average station spacing here, for example, is still around 50 kilometres. So it's not ideal for measuring how strain is localised onto individual structures. So one of the things we've been doing is trying to use INSAR to actually map that tectonic strain at a much higher spatial resolution, so using the imaging techniques. How accurately do we need to do it to make those measurements to be useful? This is a rather gruesome histogram. It's basically correlating that low-resolution map of tectonic strain against where people die in earthquakes, and it's a cumulative histogram. But essentially, 96% of all earthquake deaths are in regions with strain rates greater than 10 to the minus 8 per year. So that's a millimetre per year over 100 kilometres. So these are tiny motions, actually. And 3/4 of fatalities are where deformation rates are less than 5 millimetres a year over those 100 kilometre length scales. So we've got to be able to measure this really precisely to be able to be useful. We've been for a long time using the North Anatolian Fault as a test case. This is where I started work during my PhD 20 years ago. And it's a really nice test case because it's a long, relatively straight rupture that's oriented well for these techniques. It has a relatively high slip rate of 20 to 30 millimetres per year, and the strain is quite focused in a 50-kilometre region around the fault. And this is the work I did in my PhD. So this is one PhD's worth of work. 20 years ago, we were able to get this map showing this changing colour across the fault. So we were able to pick up the relative motion there. Red's some motion towards the satellite, blue's a motion away from the satellite. It's mostly horizontal here, but actually what you see is the projection of the 3D velocity vector into the line of sight. So you're able to see horizontal motions. So we were pretty proud of that. 10 years later or so, so these are on the same scale now. My PhD student, Richard Walters, did about 250,000 square kilometres of eastern Turkey. And then I've just had a PhD student finish, Ekbal Hussain, who's looked at all of Turkey, about 750,000 square kilometres. And that was about a PhD's worth of effort. More recently, we've taken data from Sentinel-1 and completely automatically processed the whole of Turkey and got a result. It's still a bit noisy because there's about 2 years of data, 18 months to 2 years of data gone into this. But you can see that changing colour across the fault very nicely. So we're moving to the point where we can do this completely automatically. And we're now processing the entire Alpine Himalayan belt. So watch this space. We should have results within the next year or two showing the deformation at this high resolution over the entire region. So it's come on incredibly quickly. So our ambition is to monitor all of the Earth's tectonic and volcanic zones. We're gradually switching on volcanoes, and they should all be monitored by the end of the year. Ends up being about 70 million square kilometres. And it's huge volumes of data. So this relies on big supercomputers. We use a facility at Jasmine at Harwell to do this processing. We're using about 0.5 terabyte per day. The Sentinel-1 system is producing about 12 terabytes of data every day just from that one satellite system. It's a twin satellite, so it's a huge volume of data that we're... So the only way you can do something useful is to do this completely automatically. We haven't got enough PhD students to put them all on different areas. So I thought I'd end by being a bit more parochial and zooming in on London. So I've talked about tectonic motions with these techniques, but actually the Earth is deforming for all sorts of other reasons. And the nice thing about INSAR is you can go right down to the kind of building scale deformation. So this is a high-resolution map we've made of London from data from Sentinel-1. If we just zoom in on this area, the eagle-eyed amongst you will see that sort of faint line running through the data, just coming off the northeast corner of Hyde Park. That's the Crossrail track. You can see each of the dots there is a station, and you can see where they've obviously done more tunnelling around the station sites. So you can see that they've subsided by, just in this observation period, by about 1 centimetre. So all sorts of interesting signals there. Good news is that we're here, right? And we seem to be okay. So we're off that track. Okay. So I will leave it there and conclude. So the data we're getting now are really spectacular. They're accurate and abundant, and there's huge amounts of science that we can do with these fantastic data sets. We can respond to earthquakes and volcanic unrest very rapidly, and we're still learning new things about how the Earth behaves in these events. And we're on the brink of being able to do this long-term, near real-time monitoring of deformation at tectonic and volcanic zones. Thank you very much.
Thank you so much, Tim. We have a couple of minutes for questions. Yeah, and then...
A wonderful presentation and very enlightening. I think I'll be going home and see if my house has subsided with the data we can get.
Send me the postcode, I'll let you know.
The one thing I noticed with the earlier presentation from Superdan was the difference of earthquakes causing differences in data, which I guess was a piezoelectric effect. Have you looked into that areas at all and see anything?
Yeah, so the ionosphere is noise for us. So I'm going to be very, if he's still here, I'll be very interested in having a conversation over a glass of wine about that, because it's noise for us, but we do see beautiful ionospheric signals, and actually we've been developing methods for solving for that and removing it. The ionospheric delays we get, the ionospheric phase changes are proportional to the frequency squared. So if you split the frequency of the radar signals, you can then invert for the amount of ionospheric delay. And so in principle, we get snapshots from the INSAR. From GPS, you can get beautiful time series. So I've seen movies for the Japan earthquake where you see the ionospheric waves radiating out from GPS sites, because Japan is essentially, you can't walk in Japan without tripping over a GPS site. It's full of data, and so you've got then a measurement between each GPS satellite and each GPS station of the delay, and so you can get these beautiful maps of how those ionospheric waves propagate, and it'd be very interesting to chat with somebody who might be able to use those data.
Could I just ask you about, on the London map, there was
Yes.
a cluster of points south of the river, was there not?
Okay, you don't, just here.
Yes.
Yeah, so that's the oval. The oval is there, and this is Kennington Park. I'm not really sure what it is. I mean, I googled it. So what? Sorry.
Northern Line extension?
I don't think they've started.
No, I don't think it. So
They're tunnelling that now.
maybe it is, but it seems quite a broad signal. When I googled it, the only thing I could find was there was a news story from a couple of years ago with a big burst water main there, and I just wonder whether there is some kind of movement there. The other signal you might have noticed here, this is around Canary Wharf, and that's the rebound from all the money that's gone off to Europe after Brexit.
At the back.
Thank you very much. I guess with GPS, you've got to have a solid rock anchor or go down to base rock. But when there's a lot of synthetic aperture radar looking down at the Earth, is that reflecting off the rock layer? Because the soil layers above are quite variable in height with flooding and evaporation and all sorts of things. And I've heard about these fluidized beds. Are they being picked up? And the connection of those to the earthquakes? Are you picking that fluid movement up at all?
Yeah, so what you need for the technique to work is the scattering characteristics to remain constant in your pixel, or nearly constant in your pixel between your two images. So it's a relatively short wavelength, and if the soil's wet, it will come off more or less the surface, and if that soil is undisturbed, you'll get a signal back. If things are moving around, if a farmer ploughs his field, or if you get liquefaction from soils liquefying and moving around, then the phase measurement becomes meaningless. You get an incoherent measurement. There are other things you can do to make measurements in those locations, but they're not as precise as the INSAR. So the other places it doesn't work on water. Obviously, the water surface is constantly changing. If vegetation is extremely dense in rainforest, it also struggles. The radar comes in, it scatters around the forest canopy, and then comes back with essentially a random phase number. So it doesn't work everywhere. But with systems like Sentinel-1, with the short revisit times, we're getting better and better. The ground is more and more stable. If you're looking every 6 days, not that much changes unless you have a big event. Yeah.
So, last question over there, Kathy Whaler.
Thanks very much, Tim. I was wondering, given what you said about the faults jumping much further than we'd previously thought in the New Zealand earthquake, whether there are implications for our understanding of what an aftershock is, and whether that affects how we understand, the tectonic cycle and rebound and relaxation of strain and so on.
Yeah, and I think there's lots of interesting work going on now. I'm trying to understand what aftershocks really are. So traditionally, aftershocks have a rather arbitrary definition, right? So you say it's an earthquake that happens, it's smaller than the first earthquake, it happens within a fault length of the original rupture. It's a rather arbitrary decision. Now we're seeing all sorts of interesting dynamic effects. So there's an example I didn't show from Pakistan, where there was basically an earthquake doublet. The second earthquake was triggered by the P wave from the first earthquake, 50 kilometers away. So essentially instantaneous, happened at 19 seconds apart, these two earthquakes. So do you call that an aftershock or a triggered event? So I think we tend to talk about triggered events. And of course the aftershocks might be bigger as well. They don't have to be smaller. So and there's some really interesting data coming out of Italy that's also looking at how fluids are moving after the earthquake, and you can see these kind of migrating patterns of aftershocks that seem to be triggered by the fluids movement.
Okay, well, thank you all very much, and can we again thank Tim very much.